Yes. Today we'll start with curve tracing. We'll be discussing type 1 equations in Cartesian form. Equation in Cartesian form means the equations which are in terms of x and y. Now we'll come across two types of relations, explicit relation and implicit relations. Explicit relation means relation which can be expressed in this form: y is some function of x, y is f of x, or which can be expressed in the form x is function of y, x is equal to f of y. So the given equation may be in explicit form or it can be in implicit form. It can be in the form f of x comma y is 0. All terms of x and y will be on the right hand side or left hand side of the equation, and right hand side will be 0. So we'll discuss both types. Now some basics we'll discuss before we start with curve tracing. Now we know that this is our x-axis. Equation of x-axis is given by y is 0. The vertical axis is y-axis. Equation of y-axis is given by x is equal to 0. We know that the intersection of x-axis and y-axis is the origin. Its coordinates are 0 comma 0. In first quadrant both x and y coordinates are positive. In second quadrant x is negative, y is positive. In third quadrant both x and y are negative. Fourth quadrant x is positive, y is negative. Equation of x-axis is y0, equation of y-axis is x is 0. This is our x-axis, equation of that is y0. This is our y-axis, equation of y-axis we know is x is 0. Intersection of these two axes is the origin 0 comma 0. Now remember that any line which is parallel to x-axis, equation of that line will be in the form, say y is equal to b. Say for example y is 1, y is 2. All these lines y is equal to 1, y is equal to 2 will be parallel to y is 0, and that will be drawn above the x-axis. Similarly, y is equal to minus b represents a line which is parallel to x-axis, which is parallel to the line y is equal to 0. When y is minus b, it will be a line which is parallel to x-axis, but it will be below x-axis. Similarly, we know that x is 0 represents the y-axis, and x is equal to plus a will represent a line which is parallel to y-axis, and it will be on the right hand side of y-axis. Similarly, x is equal to minus a represents a line which is parallel to y-axis, and it will be on the left hand side of the y-axis. Remember that slope of x-axis and any line which is parallel to x-axis is 0. Slope of x-axis is 0. That means dy by dx for x-axis, and any line which is parallel to x-axis, for that dy by dx is 0. Slope of y-axis and any line which is parallel to y-axis is infinity. That means dy by dx will be infinity for y-axis as well as a line which is parallel to y-axis. Now we know that slope of the line y is equal to x is 1. Remember, slope of the line y is equal to x is 1. That is dy by dx is 1. Now this line y is x is important line. This is this line. Y is equal to x is a line which passes through the origin, makes 45-degree angle with the x-axis. So line y is equal to x makes 45-degree angle with the x-axis. It passes through the origin and its slope is 1. Dy by dx is 1. Similarly, slope of the line y is minus x is minus 1. See, y is minus x is again a line which passes through the origin, makes 45-degree angle with x-axis. It passes through the second quadrant. Okay, so for that line y is equal to minus x, slope is minus 1. So this y is x, y is minus x are important lines. We should know their equations. Now, yes, we'll see what is node. See, if at a double point, so what is a double point? See, if two branches of the same curve are passing through some same point, then we'll call it as a double point. Now, if at a double point we get two different or distinct tangents, so see, this is suppose the first branch of the curve, this is the second branch of the curve, and at the point of intersection we are having two tangents available, one as t1 and second as t2. So at the point of intersection or at the double point, if we have two different or two distinct tangents, then that point will be called as a node. Yes. And now we'll see the rules to trace the curve. So we'll discuss the rules to trace the Cartesian curve, the equation which is in terms of x and y. Now the first rule is about symmetry. Rule 1 is for symmetry. If there are only even powers of y in the given equation, if there are only even powers of y in the equation, there are no odd power of y, or there are no fraction powers of y in the equation. So no power of y like y raised to half, etc. And there are only even powers of y in the equation like y square, y raised to 4, etc. Then the curve is symmetric about the x-axis. If there are only even powers of y in the equation, then the curve will be symmetric about the x-axis. For example, the standard example of parabola, if we consider, we know the equation of the parabola y square is x. Observe that in this equation we have only even power of y. There is y square in the equation. There is no odd power of y. Or there is no term like y raised to half or y cube, etc. We have only one even power of y, that is y square. If you have only even power of y in a given equation, then that curve is symmetric about the x-axis. So how to draw that we'll see later on. The important part is just to check what is the symmetry. Now here the curve is symmetric about the x-axis because there are only even powers of y. That means whatever is the nature of the curve above x-axis, same is the nature of the curve below x-axis. Or you can say that the nature of the curve below x-axis is the mirror image of the curve above the x-axis. Another example, if we consider this equation y square is equal to x raised to 5 into 2a minus x. See, I just want to tell you how to identify the symmetry, how to draw the curve, we'll see later on. Now, if you observe this equation, we can see that there are only even powers of y, that is y square in the equation. There is no odd power. There is no term like y cube, y raised to 1, y raised to 5, etc. There is no fractional power of y like y raised to half, y raised to 1 by 3, etc. We have only even power of y. So that's why the curve is symmetric about the x-axis. Whatever is the nature of the curve above x-axis, same is the nature of the curve below x-axis. Okay, so or in other words, you can say that nature of the curve below x-axis is the mirror image of the curve which is above the x-axis. Now, if you have to consider the symmetry about y-axis, if there are only even powers of x in the equation, if there are only even powers of x in the given equation, then the curve is symmetric about the y-axis. So see, what is the symmetry about y-axis? That in the given equation we should have only even powers of x. There should be no odd power of x. There should be no term like x raised to 1, x cube, etc. There should be no fractional power of x like x raised to half, x raised to 1 by 3, etc. If there are only even powers of x in the equation, curve will be symmetric about the y-axis. Like for example, consider again this famous example of parabola. We know this curve x square is equal to y. In this curve we have only even power of x, that is x square. So if there is only even power of x in the given equation, curve will be symmetric about y-axis. That means whatever is the nature of the curve on the left hand side of y-axis, same will be nature of the curve on the right hand side of y-axis. Then consider this example, y into bracket x square plus 4a square is equal to 8a cube. See, we just want to see what is the nature of the curve or what is the symmetry of this curve. You can observe that in this equation we have only even power of x. There is no odd power of x like x raised to 1, etc. There is only even power of x in the equation. There is no odd power of x in the equation. So we can say that the curve is symmetric about the y-axis. The curve is symmetric about y-axis. So whatever is going to be the nature of the curve on the left hand side of y-axis, same will be on the right hand side. So here, see, I have not discussed how to draw the curve. We'll see in the later part. But for timing, you just understand that this curve is symmetric about y-axis because there are only even powers of x in the given equation. Then, see if this, the next rule that if, again this is about symmetry, if there are only even powers of both x and y in the equation, in a given equation, if you have only even powers of x and even powers of y, there is no odd power of x, there is no odd power of y, or there is no fractional power of x or y in the equation, then the curve is symmetric about both x and y axis. So see, for example, if you have an equation of the curve of this form, x square plus y square is a square. So this is a basic simple example of a circle, standard circle. X square plus y square is a square. We know that is the equation of a circle with center at origin. We can see that there are only even powers of x and y in the equation. In this given circle, there are only even powers of x and y. There is no odd power of x, there is no odd power of y. So therefore, the curve is symmetric about both x and y axis. Similarly, if you consider another example, of the curve a square into y square is equal to x square into bracket a square minus x square. You can observe that in this equation, again, there are only even powers of x and y in the equation. There is no odd power of x, there is no odd power of y. So this curve is symmetric about x as well as y axis. Whatever is the nature of the curve on the left hand side of y axis, same is the nature on the right hand side of y axis. Whatever is the nature of the curve above x axis, same is going to be the nature below x axis. So this curve is symmetric about both x and y axis. Now, if again for symmetry, if we see that if in a given equation, if that given equation remains unchanged, even if we replace x by minus x and y by minus y, then the curve is symmetric in opposite quadrants. What does this rule tells us? That if in a given equation, in place of x, if you write minus x, in place of y, you write minus y, and still the equation does not change, then the curve is symmetric in opposite quadrants. Like for example, if you take the example of this curve, y is equal to x cube. In this equation, in place of y, if you write minus y, and in place of x, if you write minus x, then see what happens. This becomes minus y is equal to cube of minus x. So simplifying further, you will get again y is equal to x cube. That minus minus sign gets cancelled from both the sides, and it still remains y is equal to x cube. Y is equal to x cube. So you can see that even if you replace y by minus y, x by minus x, the equation does not change. The equation remains same. In such case, the curve is symmetric in the opposite quadrants. Whatever is the nature of the curve in the first quadrant, same will be nature of the curve in the third quadrant. So, or in other words, the nature of the curve in the third quadrant is the mirror image of the curve in the first quadrant. Or I'll give another example, again a famous example of ellipse. You consider this equation x square upon a square plus y square upon b square is 1. In this equation, if you replace x by minus x, square of minus x will be x square. If you replace y by minus y, square of minus y is again plus y square. So the equation does not change if you replace x by minus x, y by minus y. So according to our rule, the curve is symmetric in opposite quadrant. That means whatever is the nature of the curve in the first quadrant, same is the nature of the curve in the third quadrant. Or whatever is the nature of the curve in the second quadrant, same is the nature of the curve in the fourth quadrant. So the curve is symmetric in opposite quadrants according to the rule. Then the next rule to check symmetry is that if the equation remains unchanged, even if we replace x by y and y by x, then the curve is symmetric about the line y is equal to x. What does this rule tells us? That if you replace x by y, wherever there is x, if you replace it by y, and y if you replace by x, like in this example, the equation is x into y is c. We know that is a hyperbola, which we'll study in graphics. So if we replace x by y, in place of x I am writing y, and in place of y I am writing x. So that equation x into y is c now becomes y into x is equal to c. The equation does not change, it remains same. X into y is c is same as y into x is c. So according to this rule, the curve is symmetric about the line y is equal to x. Remember, we know that this line y is equal to x is a line which passes through the origin, which makes 45-degree angle with x as well as y axis, and it passes through the first quadrant. Now the curve here is symmetric about this line y is equal to x. So whatever is the nature of the curve above this line y is x, same is the nature of the curve below the line y is x. Then if you consider the standard circle again, x square plus y square is a square. So see, if you replace x by y, y by x, this equation will be y square plus x square is a square. The equation remains the same. So this curve is symmetric about the line y is x. So whatever is the nature of the curve above the line y is x, same is the nature of the curve below the line y is x. Then the next rule to check symmetry is that if the equation remains unchanged, even if we replace x by minus y and y by minus x, then the curve is symmetric about the line y is minus x. So see, according to this rule, in place of x, if you replace it by minus y, in place of y, if you replace it by minus x, then the curve will be symmetric about the, and if again still the equation does not change, then it is symmetric about the line y is minus x. Again, we'll take a simple example of the circle, standard circle, x square plus y square is a square. In place of x, if you write minus y, replace this x by minus y, it will be square of minus y. In place of y, if you replace it by minus x, it becomes y square plus x square is a square. If you replace x by minus y, y by minus x, you'll find that the equation does not change, it remains the same. This curve will find is symmetric about the line y is minus x. So this circle we know is symmetric about line y is minus x. Whatever is the nature of the curve above the line y is minus x is same below y is minus x. Remember, the curve can have more than one symmetry. Like this example, standard circle is symmetric about x axis, y axis. It is symmetric about y is x, symmetric about y is minus x. Yes, now the next rules to check whether the curve passes through the origin. We know that x and y coordinate of the origin are 0. Now, to check whether the curve passes through the origin, see, first thing what we can do is we can put x is 0 in the given equation and check whether y becomes 0 at the same time. So if you put x is 0 in the given equation and y also becomes 0, then we can see that the curve passes through the origin. Again, if you take the simple example of this parabola, y square is equal to x. In this equation, if I put x is 0, we'll get y square is 0, we'll get y is 0. So when x is 0, y is 0, we know that this curve parabola passes through the origin 0, 0. Or we can do vice versa. If you put y is 0 in the given equation and x becomes 0, then we can say curve passes through the origin. Like see, for example, in this equation, if I put y is 0, I'll get x square is 0, x square is 0, so x is 0. So when x is 0, y is 0, or when y is 0, x is 0. So here this curve also passes through the origin 0, 0. Remember that the curve does not pass through the origin if there is a absolute constant in the equation. If there is an absolute constant, that means the constant which is not multiplied by any variable like x or y. In that case, the curve will not pass through the origin. You see, what does this rule or this note tells us? That the curve does not pass through the origin if there is an absolute constant in the equation. Like for example, this equation x square plus y square is 4. Again, it is the equation of a standard circle, we know. So here this 4 is an absolute constant. Is an absolute constant. See, because see this curve, we can see that this constant is absolute constant first of all, because this constant 4 is not multiplied by any variable like x or y. This kind of constant we call it as an absolute constant, and if that kind of constant is there in the equation, the curve will not pass through origin. See, if you put x is 0, we'll get y square is 4, y is 2. So when x is 0, y is not 0, or if you put y is 0, you will get x square is 4, so x is 2, x is plus or minus 2, you will get. So the curve does not pass through the origin. Correct. The point origin is inside the curve, but it is not lying on the curve. Remember. So if there is an absolute constant in the equation, the curve is not going to pass through the origin. Then, if the curve passes through the origin, the next rule that we should check for is to find the tangent at origin. We check for this rule only if the curve passes through the origin. Now to find tangent at origin, see what we have to do. We have to equate the lowest degree term in the equation or lowest degree terms taken together in the equation with 0. Like for example, this equation you consider y square is equal to x. We'll consider a simple example of a parabola. The standard curve, we know y square is equal to x. So in this equation, we know that this curve passes through the origin. If I put y is 0, we'll get x is 0. The curve passes through the origin. We want to find what is the tangent at origin. See, to find tangent at origin, if we put, say, like first of all, let us check the degree of these terms. X raised to 1 degree is 1, x raised to 1 degree is 1, y square degree is 2. Now see which is the lowest degree term taken in this equation. See, x is the lowest degree term. It is a term with degree 1. Okay, there is no other term of degree 1 in this equation. Also, there is no other term with degree less than 1 in this equation. So to find tangent at origin, we have to equate the lowest degree term in the equation with 0. So here in this case, it is x. If we equate x with 0, we will get x is 0. So x is 0. That is nothing but the y-axis. Y-axis is the tangent at origin. You can see that x is 0 is the tangent at origin in this case. Then Another example where we can find tangent at origin. See this curve, y square into 2a minus x is equal to x cube. If I open this bracket, it is 2a y square minus x into y square is x cube. Note that here there is no absolute constant in the equation. 2a is a constant, but it is multiplied with y square. So there it is not, we cannot call it as an absolute constant. So there is no absolute constant in the equation. The curve is going to pass through the origin. Or you can see that if I put y is 0, x also becomes 0. So we'll have to find tangent at origin. To find tangent at origin, we find degree of different terms in this equation. X cube, see x cube, degree of x cube is 3. X into y square, degree is 3. Why it is 3? Because it is x raised to 1 into y square. Whenever it is multiplication of terms, we add the powers to find the degree. So it is x raised to 1 into y square. The degree will be 3. 1 plus 2, the degree becomes 3. When it is multiplication of terms, we add the powers to find the degree. Or when it is division of the terms, we subtract the powers to find degree. Now this term 2a into y square, see its degree is 2. 2a is a constant. Degree of 2a you can consider 0. So 0 plus 2 is 2 square. So it is 2a into y square. So degree of that is 2. The lowest degree term in this equation is 2a y square. Find tangent at origin, we equate the lowest degree term in the equation with 0. Lowest degree term in the equation is 2a y square. That we equate with 0. Find tangent at origin. 2a is 0 is meaningless. So, or you can say that y square will be 0 upon 2a. So, it will be 0. We are not considering 2 as 0 because it is a constant, some non-zero constant. So, we get y square is 0 or we get y into y is 0. So, we get y is 0. That is the x-axis is tangent at origin. Remember y is 0 is equation of x-axis. So, here x-axis is the tangent at origin. Also, you will note that in this case, we'll get y0 two times. Y0 two times. So that means two times that x-axis is tangent to the curve. So this kind of point is called as a cusp. So if two branches have the same common tangent at a given point, then that point is called as a cusp. So how to draw that, we'll see later on. For timing, you just remember that if there are two coincident tangents, the same point of the curve, then that point is called as a cusp. Then another example where we find tangent at origin, we'll see one more example of this kind. We consider this equation, x square into y square is equal to 4 into bracket y square minus x square. If you open the brackets and check the degrees of all these terms, x square into y square, degree is 4, x square into y square, 2 plus 2, degree will be 4. 4y square, degree is 2, remember 4 is a constant, 4 into y square, degree of that term becomes 2 because 4, the degree is 0, any constant degree is 0. So 0 plus 2 will be 2. So degree of 4y square is 0. Similarly, degree of 4x square is 2. Now to find tangent at origin, we have to equate the lowest degree term with 0. And again before that, see, remember, we will find tangent in this case because the curve is going to pass through the origin. There is no absolute constant in the equation. So the curve is going to pass through origin. Here 4 is a constant, but it is not absolute constant because it is multiplied with y square minus x square. The curve will pass through the origin. And now to find tangent at origin, we equate the lowest degree term in the equation with 0 or lowest degree terms taken together in the equation with 0. We can observe that here these two terms 4y square minus 4x square, their degree is 2 and there is no other term in the equation with degree less than 2. So this is the lowest degree term. This 4y square minus 4x square is the lowest degree term in the equation. That terms we take together, we equate with 0. Divide this whole equation by 4. This 4y square minus 4x square is 0. If you divide by 4, you will get y square minus x square is 0. You get y minus x into y plus x is 0. Equating these two brackets with 0, we'll get y minus x is 0 and y plus x is 0. We get y is x and y is minus x as the tangent at origin. So these two lines, y is x, y is minus x, in this case will be tangent at origin. So we know that y is x is this line which passes through the origin and makes 45-degree angle with x-axis. Similarly, y is minus x is the tangent at origin. So how to make use of this rule, we'll see while discussing the problems itself. We just found out how we can find the tangents at origin for the given curve. Now, yes, again, one more example where we can find tangent at origin. So see, if you consider this equation, y square into bracket a square minus x square is a cube x. You consider this equation. Our aim is just to find tangent at origin. Now, if you open the brackets, this equation becomes a square into y square minus y square into x square is a cube x. The degree of this term a square into y square is 2. Degree of y square into x square is 4. 2 plus 2, the degree will be 4. A cube x, degree is 1. Remember, a cube is a constant. Degree of that is considered as 0. So 0 plus 1, it is x. So it is x raised to 1. Degree of that becomes 1. The lowest degree term in this equation is a cube x. We equate the lowest degree term with 0 to find tangent at origin. If we equate a cube x with 0, we'll get x is 0 upon a cube, that is 0. So we get x is 0. X is 0 is, remember, the equation of y-axis. So in this case, y-axis is x is 0 will be tangent to the curve at origin. So that is the tangent at origin. Now the next rule that we will discuss is to find asymptote. This next rule, rule 4, is to find asymptote. Now what is asymptote? Remember, asymptotes are tangent to the curve at infinity. Asymptotes are tangent to the curve at infinity. Or in simple words, asymptote is a line which will run parallel to the curve, or the curve runs parallel to the asymptote. It will never touch the asymptote. The curve touch the asymptotes only at infinity. So theoretically it will touch the asymptote at infinity. For example, suppose for this curve x is equal to a is an asymptote. The curve runs parallel to that line and it will never touch that line. Or in this example, see, this x-axis as well as y-axis is the asymptote. So the curve runs parallel to x and y-axis. How to find that? We'll see now. Yes. First of all, to find asymptote parallel to x-axis, if you have to find asymptote parallel to x-axis, then we have to equate to 0 the coefficient of highest degree term in x. So see, if you want to find asymptote parallel to x-axis, what we have to do? 0. What we have to do? We have to equate to 0. We have to equate to 0 what? Coefficient of what? Highest degree term in x in the given equation. Like for example, if you consider this equation, y into bracket x square plus 4a square is equal to 8a cube. Now to find asymptote parallel to x-axis, what I have done, I have first of all expanded the bracket. This becomes y into x square plus 4a square, y is 8a cube. Now you can see that there is only one term of x, that is x square in this equation. X square is the only term of x in this equation, and that is the highest degree term in x. And coefficient of this term is y. We have to equate the coefficient of highest degree term in x with 0. Here in this equation, highest degree term in x is x square. Coefficient of that is y. Y is multiplied with x square. We equate that coefficient with 0. So we get y is equal to 0. Y is 0 is nothing but the x-axis. So in this case, x-axis is the asymptote to the curve. So this line, x-axis, that is y0, is the asymptote to the curve. And how to draw the curve, that is a later part, we'll discuss it later. But from this rule, we just found out that y0, that is the x-axis, is asymptote to the curve. That means the curve is going to run parallel to the x-axis. It will never touch the x-axis, or it touches the x-axis at infinity according to the definition. And here I have drawn it in such a way because we can see that it is going to be symmetric about y-axis, because there are only even powers of x in the equation. That part we'll discuss in later while we discuss the problems. Then see this next example, we'll just check how to find asymptote parallel to x-axis. So here the equation is a square into y square is equal to x square into bracket a square minus y square. Remember, to find asymptote parallel to x-axis, we have to equate the coefficient of highest degree term in x with 0. So see here, the highest degree term in x is x square. There is only one term of x in this equation, which we can see is x square. So that is the highest degree term in x, and coefficient of this x square is a square minus y square. This coefficient of highest degree term in x, we have to equate with 0. So we equate a square minus y square with 0. And now a square minus y square can be written as a minus y into a plus y. If we equate this with 0, we get a minus y is 0 and a plus y is 0. So solving that, we get y is 0 and y is minus a. We will get two equations, y is equal to a and y is minus a. Remember, we should get some equation of this form, like y is 0, y is plus a, y is minus 1, y is minus 2, etc. If you get some constant is 0, like 1 is 0, 2 is 0, 3 is 0, then it will be meaningless. Then there will be no asymptote parallel to x-axis in that case. So here we have got two lines, y is equal to plus a and y is minus a as the asymptote. So these are the two lines which are parallel to x-axis. Y is plus a, y is minus a. These lines are asymptote. That means the curve is going to run parallel to this line. It will not touch that line. Correct? So these two lines are asymptote to the given curve. How to draw that we'll discuss later on. But now we have just discussed the rule to find the asymptote parallel to x-axis. Similarly, to find asymptote parallel to y-axis, we equate to 0 the coefficient of highest degree term in y in the given equation. So see, like for example, if you consider this example, y square into 2a minus x is x cube. See, our aim is to find asymptote parallel to y-axis. To find asymptote parallel to y-axis, we have to equate the coefficient of highest degree term in y with 0. First, find what is the highest degree term of y in the equation. In this equation, you can see that the highest degree term of y is y square. There is no other term of y in the equation with degree more than 2. So y square is the highest degree term of y in the given equation, and coefficient of that y square is 2a minus x. So y square here is, we can see that multiplied with the bracket 2a minus x. So we equate the coefficient of highest degree term in y with 0 to find asymptote parallel to y-axis. So here we get 2a minus x is 0, or we get 2a is x, or we get x is 2a. So x is 2a is the asymptote. This line x is 2a. Remember, x is 0 is the y-axis. X is 2a will be a line parallel to y-axis on the right hand side, because x is positive. Say, considering 2a as positive, it will be on the right hand side of the y-axis. Line x is 2a is the asymptote. That means the curve will run parallel to that line x is 2a. It will not touch that line. It runs parallel. According to the definition of asymptote, the curve will run parallel to the line x is 2a. And the curve is symmetric about x-axis. So whatever is the nature of the curve above x-axis, same will be the nature below x-axis. How to draw that curve we'll see later, but now we are just discussing how to find asymptote parallel to y-axis. Similarly, in this next example, y square into bracket a square minus x square is a square into x square. So this example, our aim is to find asymptote parallel to y-axis. For that, we see what is the highest degree term of y in the equation. You can see that there is only one term of y, that is y square. Coefficient of y square is a square minus x square. You see, highest degree term in y in this equation is y square. Coefficient of that is a square minus x square. We equate the coefficient with 0. We have to equate the coefficient of highest degree term in y with 0. This is the coefficient a square minus x square, that we equate with 0. Simplifying, we get a plus x into a minus x is 0. If we equate a minus x with 0, we get x is a. If we equate a plus x with 0, we get x is minus a. So in this case, these two lines, x is plus a and x is minus a, are the asymptotes parallel to the y-axis. Remember, this is our y-axis, that is x is 0. X is plus a will be on the right hand side of y-axis, whereas x is minus a will be on the left hand side of y-axis. And our curve in this case is going to run parallel to both x is a as well as x is minus a, because they are the asymptote. You'll observe that this curve is symmetric about both x and y axis. So whatever is the nature of the curve above x axis, same will be the nature of the curve below x axis.